Welcome to my channel. Hubble pointed at Earth, what it really sees. Point Hubble at Earth, and see what it captures. Hubble orbits 570 kilometers above Earth with 0.05 arcsecond diffraction limit. Theoretically, it resolves objects as small as 15 centimeters, roughly the size of a bowl. At this resolution, it sees individual cars, distinguishes large animal shapes, and shows clear trees and roofs, but not license plates. This 15 centimeters resolution only applies to ideal theoretical conditions. In reality, photos taken by Hubble pointing down are completely useless. Speed is the main issue. Hubble travels at 27,000 kilometers per hour. Ground below passes by nearly 8 kilometers every second. Even 0.01 second exposure stretches ground into 70-meter-long blurry streaks and destroys all details. Freezing motion at 15 centimeters resolution requires roughly 20 microsecond exposure. That is thousands of times faster than Hubble camera's fastest shutter speed. These telescopes use slow, sensitive scientific sensors, designed for hours-long continuous galaxy observations, not instant action camera shots. Hubble cannot track ground by rotating. It would need to spin extremely fast, but its maximum rotation speed matches clock-minute hands, far too slow to keep up with passing ground. Downward viewing also requires passing through entire Earth atmosphere. Turbulent air between telescope and ground blurs images completely. Same as issues faced by ground-based observatories looking up. Daytime Earth's surface also shines blindingly bright, compared to faint galaxies Hubble normally photographs. This could easily damage its sensitive detectors. NASA knows all this well, and explicitly states Hubble cannot observe Earth. What they do not say is, US military had better spy satellite telescopes decades before Hubble launched. NASA originally planned 3-meter primary mirror for Hubble, then switched to 2.4 meters. Official reason was cost saving, but real reason was military had years of experience building mirrors this size for their spy satellites. US began launching KH-11 Kennen satellites in December 1976. These satellites also carry 2.4-meter diameter primary mirrors, identical to Hubble's, but point straight at Earth, not stars. These satellites solved all Hubble's problems from design start. They have ultra-short exposure times, electronic motion compensation, and ability to transmit clear digital images back to Earth nearly in real time. Thus, spy satellites inspired Hubble, not the other way around. In 2012, National Reconnaissance Office, the secret agency building US spy satellites, donated to spare 2.4-meter primary mirror telescope assemblies to NASA. 2 complete, unused Hubble-class space telescopes sat gathering dust in warehouses. Astronomy community was shocked. One donated telescope is now being converted into Nancy Grace Roman Space Telescope. Before these digital spy satellites, earlier generation spy satellites amazed people in another way. In 1960s, Corona satellites photographed Soviet Union using actual film, then ejected film canisters back to Earth. Military planes caught these canisters mid-air with hooks, as they parachuted over Pacific Ocean. Uncaught canisters self-destructed and sank to Pacific Ocean floor. Now we ask, what resolution today's most advanced spy satellites achieve? In August 2019, an Iranian rocket exploded on launch pad. A satellite photograph appeared shortly after. Amateur satellite trackers confirmed this photo almost certainly came from a KH-11 satellite. It passed over Iran at exactly the right time. Analysts compared photo features to known buildings and estimated resolution at roughly 10 cm. Even 10 centimeters resolution is far too low to read text or recognize human faces. A person appears as small cluster of pixels. You can tell it is a person, but not who it is. Classic zoom and enhance trick from movies remains pure fiction. No computer can create non-existent details if an object is only 2 pixels wide. No satellite can stare continuously at same location. They orbit Earth every 90 minutes, and pass over any given location for only few minutes. Hollywood scenes of real-time car tracking through city streets from orbit remain pure science fiction. So what happens when we point Hubble at Earth? Literal answer is, you get bright, blurry, completely useless photo. Hubble was never built for this job. But real answer is far more interesting. Mirror technology and optical principles that let Hubble photograph galaxies billions of light-years away, developed secretly in parallel during Cold War. Their ultimate goal was to monitor our own planet. Good news is, satellites operated by commercial companies now achieve 30 centimeters resolution. Anyone can purchase and use them. Technology once top secret during Cold War is now becoming commonplace. but physical laws limiting all these systems, diffraction, atmosphere, orbital mechanics, ensure no telescope, no matter how expensive, will ever give anyone omniscient power from orbit. Thin atmosphere that makes stars twinkle also blurs all downward-looking views. Nature has drawn a small privacy curtain for us. Honestly, I find that quite reassuring. This shift from military secrecy to public accessibility represents one of the most remarkable transformations in space history. Today, anyone with an internet connection can view high-resolution images of almost any place on Earth. We use these tools to track wildfires, monitor glacial retreat, and assess damage after earthquakes and hurricanes. These capabilities have saved countless lives and helped us understand our planet in ways never before possible. But this same technology also raises important questions about privacy and surveillance. As satellite resolution continues to improve, we must find a balance between the benefits of global observation and the right to personal privacy. Physical laws will always set hard limits on what any satellite can see, but human laws must set limits on how these tools are used. The story of Hubble and spy satellites reminds us that technology itself is neutral. It can be used to peer into the farthest corners of the universe, or to watch our own planet from above. The choice always lies with us. We can continue to reach for the stars, while also protecting the small moments of privacy that make us human. That balance between exploration and protection is perhaps the most important lesson we can learn from these incredible machines. Thank you for watching, and see you next time.